In our final video in our series about stellar evolution, we're going to look at what happens to the core of a supergiant star after a supernova has destroyed the rest of the star. Well, the first possibility is that if the supernova is destructive enough, the core of the star is actually destroyed with the rest of the star itself, and the gas and energy that makes up the core of the star is simply scattered along with the rest of these stellar remnants into deep space, which can then recondense into a nebula in order to form a new star, as we talked about in the previous video. However, what we're going to focus on in this video are the two possibilities of what happens should the core manage to survive. And the first of those possibilities results in the dead star's core forming a type of star that we call a neutron star. So neutron stars are similar to white dwarfs in that they compose a small remnant of the star's core, but whereas a white dwarf is maybe the size of a small planet, neutron stars are usually even smaller, often being not much bigger than a larger than average city on Earth. However, they have an even stronger gravitational force than white dwarfs. Imagine the mass of a red supergiant star condensed into a volume that is no bigger than a large city on Earth. This means that neutron stars have the second highest densities of any object that exists within deep space. Just to put a number to this, neutron stars have densities that are more than 1 trillion times, which is 10 to the exponent 12, denser than our sun's density. So just to give you an idea about how big the number 1 trillion is, take a 1 and add 12 zeros to it. This is how much more dense a neutron star is compared to our sun. Now, the horrors of what make neutron stars some of the scariest objects that exist in deep space only begins with their extremely strong gravitational pulls, because neutron stars also have very, very strong magnetic fields. In fact, neutron stars that have particularly strong magnetic fields, like the ones that we see visually extending out into space like this, these forms of neutron stars are what we call magnetars, and a magnetar was recently discovered and studied by a group of Canadian astronomers, so you can read about this in the news. The magnetic fields of neutron stars make them very interesting for astronomers to study, because these magnetic fields seem to result in random radio waves being broadcasted into space. Now, in addition to these strong magnetic fields, we can see, if we look at the poles of this neutron star, we can see that there are jets of radiation that are shooting out in either direction, and this form of radiation is usually a combination of X-rays and gamma rays, which are the deadliest forms of radiation, each of which can give humans a very bad case of cancer. Now, the amount of radiation that is being shot out of a neutron star would be enough to kill every living thing on a planet that is close by. And these jets of radiation shooting out from the neutron star are what we call pulsars. So as terrifying as neutron stars may be, they pale in comparison to the other object that might be formed after a supernova after a supernova results in the death of a supergiant star, and that, of course, are black holes. So if the core of a supergiant star does not become a neutron star, they might instead become a black hole, which are terrifying because they are known to have the strongest gravitational force of any known object in space. The gravity of a black hole is so strong that any matter that gets close to it, or even any form of energy that gets close to it, is going to be pulled closer into the center of the black hole. And in this diagram, we can actually see all of the energy and matter being pulled into the black hole, forming this disc-like structure or ring-like structure around the black hole called an accretion disk. Now, if you were unlucky enough to get caught in the accretion disk, there is still an unlikely possibility that you would be able to escape if you were moving fast enough to get away from the gravitational pull of a black hole. However, once you reached the apparently solid black structure of the black hole, which is a structure that we call the event horizon, this is the point of no return, literally. Any object that passes through the event horizon of a black hole will no longer be able to escape the black hole's gravity and will instead become part of the mass of the black hole, and meaning that the more matter and energy a black hole absorbs, the bigger it will get and the stronger its gravitational force will get. Now, if we go all the way to the theoretical center of a black hole, you would reach a single point where all of the matter that is being absorbed by the black hole, as well as all of the energy and even the very concept of time, would all exist condensed onto a single point that we call a singularity. This is a very difficult thing to imagine because basically you have to imagine everything that is being sucked into a black hole, including the passage of time, on a single point of matter that is no bigger than a single atom. And for this reason, this is why black holes are unrivaled in terms of their gravitational strength. Now, despite the destructive potential of a black hole, if a black hole were to appear in our solar system, its gravitational pull would cause all of the planets to get sucked into the black hole, and eventually they would become part of the structure, which is a terrifying possibility. But as we can see, black holes are actually a very necessary part of the formation of larger structures in space. So this is, of course, what we call a galaxy, and galaxies are simply large clusters of stars that all orbit around a central point at the center of a galaxy, which, not surprisingly, is what we call galactic center. So, what exactly causes this? Well, at the center of every galaxy is actually a supermassive black hole. This is a black hole with millions, if not billions of times the mass of a single star system. So if you were to take our entire solar system, the supermassive black hole at the center of our galaxy, which is what we call the Milky Way galaxy, would have a mass that is literally billions of times greater than our entire solar system. And because of the immense size and immense gravitational force of this supermassive black hole, not only is it going to hold all of the literally hundreds of billions of stars that exist within the Milky Way galaxy in this general shape, but its gravitational force is strong enough such that all of the stars in the galaxy will actually form an orbital pattern around this supermassive black hole in the same way that Earth forms an orbital pathway around our sun. This concludes our video series on stellar evolution, but by no means should this be your last exploration of the cosmic horrors and also cosmic beauty that we find within deep space.